My name is Bo, and I'm here to talk to you about aircraft flight instruments and navigation equipment. Today's lesson objective is to determine that you have the knowledge, risk management, and skills associated with managing instruments appropriate for IFR flight. And that's going to include limitations and failure points for vacuum, electrical, and pitot-static systems. Now, when you're in IFR flight, it requires you to know how instruments are affected by system failures and how to safely fly IFR with these failures. And if we understand how these instruments operate, we can easily diagnose a failure when it occurs. This lesson is comprised of four major elements, that being the flight instrument systems, navigation systems, anti-ice and de-ice, and risk management. The flight instrument systems includes the pitot-static instrument system, the gyroscopic, which is going to include the electric and vacuum, and then we have the magnetic compass and the electrical system, which is going to include PFD and MFD, like in a G1000. Now with this mini lesson, I will get through the pitot-static instrument system, which will include the airspeed indicator. Now we have a pitot tube, which is located under the wing in most general aviation aircraft. This is a Cessna 172. And then our static air source is a little pinhole, which you can see there on the right-hand side of the screen, and that's going to give us our static air pressure for the system. The pitot tube is heated, and it can be turned on by a switch on the instrument panel, and this can help us avoid problems with icing. And when we have the aircraft on the ground, we should cover this with a cover so that bugs or debris doesn't get in there, and that we can make sure that our system will operate when we're ready to fly. And it's important to remove that cover before we fly. So we've talked about the pitot tube and the static air source, and there's also an alternate static air source, and that's actuated within the instrument panel. So on a Cessna, we have the alternate static air source, which is a little lever you pull on, and that gives us air source from inside the cabin. And on Piper series aircraft, it's below the instrument panel by your left knee, if you're sitting on the left side of the aircraft. Here's a diagram of the pitot-static instrument system, and let me get a pointer here. So we have our pitot tube, which we covered, and then we also have our static port, which is connected to three gauges. That's going to be the airspeed indicator, vertical speed indicator, and our altimeter. And we also have this alternate static source, which is inside the cabin, and we talked about how to actuate that. The pitot tube can be heated through a switch on the instrument panel, and that has these little heater elements within the tube, which will heat the entire pitot tube. Now as ram air pressure comes into the pitot tube, it builds up, and this just makes like a chamber so that if we have sudden gusts, that it kind of evens out. So our ram air pressure comes through the pitot tube, through the plumbing, and into our airspeed indicator. Now that's the only indicator that our pitot tube goes to. And then our static air source here is connected through plumbing to each one of the gauges individually. This is what the plumbing looks like. It's a good picture, so I wanted to share it with you. But the pressure is carried through the pitot and static lines, through the wing and the fuselage to this plumbing. So this is the pitot tube that we're talking about. And this is all the plumbing that it goes through, all the way to the gauge. And you can see, top left-hand panel, that's your airspeed indicator. And that's the only gauge that goes to. We have our static source right here, which is plumbed to each gauge individually. So we'll talk specifically about the airspeed indicator now. And like I said, it's the only gauge in this pitot-static system that's connected to both sources. So we have our pitot tube with that plumbing that you just saw a picture of, and that's going to go to our airspeed indicator. And then we have our static source, which is also connected to that. The way this works is our ram air is going to go in through our pitot tube, through our plumbing, and then inside the instrument case. So when you're looking at your dash, the only thing you see is the face of the gauge right there. But behind the instrument panel, there's actually an instrument case behind it. And when this air pressure comes through this tubing, and it gets plumbed right here into the back of the airspeed indicator, it's going into this diaphragm. And what that does is, as airspeed increases, we're going to have more pressure coming through our pitot tube, and that's going to expand this diaphragm. As this diaphragm expands, it's connected to a series of linkage, which in turn, as this diaphragm expands, it turns all of this, and then it shows an increase on our airspeed indicator. And the same thing happens when we decrease our airspeed or decrease the pressure. That diaphragm will get smaller and that airspeed needle will be decreasing. Now, then we have our static airline, which is also connected to this, but what that does is, you can think of this diaphragm like a balloon. We're going through the air and is blowing up a balloon. And that would be kind of difficult if this was a sealed case. And the case itself is plumbed through our static airline. And one thing that does is it keeps our airspeed indicator accurate when we climb up in altitude and the outside static air pressure changes. And I'll just make sure I covered everything here. We have ram air enters the P-dot tube and goes in the diaphragm, and our static ambient pressure fills the interior chamber, which we talked about. And then the diaphragm expands or compresses, which moves the gears with the face dial. Now essentially what this gauge is doing is it's being a differential pressure indicator. And what that means is it's always continually taking the pressure from the ram air and comparing it to the static air. So as that diaphragm increases, it's pushing against the static air inside the case. So it's reading the differential. The ram air pressure minus the static pressure is going to give us our dynamic pressure, or what's also called as total pressure. And then that's the pressure that we're actually seeing on the indicator for our airspeed. When we're talking about the airspeed indicator, I know you probably went through this with your private and maybe your commercial if you've gotten that done, but there's different types of airspeeds. We have indicated airspeed, calibrated airspeed, true airspeed, and ground speed. Now, indicated airspeed is what you're reading on the face of the gauge. That's what's indicated to you, and that's what we use for our numbers from the POH or the AFM. And it's uncorrected for variations in atmospheric density, installation air, or instrument air. Calibrated airspeed is indicated airspeed and corrected for that installation air and instrument air. So this might be the angle that the P-dot tube is mounted at. And it's usually mounted at a specific angle, so it's most accurate at cruise flight. And if you look in your POH, there's a chart for calibrated airspeed corrections. And you'll see that at cruise airspeeds, it might only be 1 or 2 knots. And at slower airspeeds, our indicated may not be as accurate just due to installation air. And it usually doesn't vary a lot. It may be 3 or 4 knots at a slow airspeed. True airspeed is the calibrated airspeed corrected for altitude and non-standard temperature. So because air density decreases with an increase in altitude, the aircraft has to be flown faster at higher altitudes. And then ultimately we have our ground speed, which is the actual speed of the airplane over the ground. And so it's true airspeed adjusted for wind. So true airspeed is how fast our airplane's actually flying through the air. And then if we're flying into a headwind, that's obviously going to where our aircraft's not traveling as fast over ground. So our ground speed is going to decrease with a headwind or increase with a tailwind. Now with the indicator, we have V speeds that we have on there, and this will just be kind of a refresher. So we have VSO, which is our stall speed with full flaps. It's the bottom of the white arc. And then we have VS1, which is the bottom of the green arc, and that's going to be flaps up stall speed. And we have our max flap extended speed, which is going to be the top of the white arc, and our white arc is our flap operating range. And we have our VNO, which is our max structural cruising speed, which is the top of the green arc. And we have our VNE, which is our never exceed speed. This is our red line right here at the top of our indicator. Now we have errors that can happen with our airspeed indicator, and this is where it's really important as an IFR pilot to be able to understand when our indicators are giving us errors, and we can kind of differentiate what's going on. So if we have a blocked P-dot tube and it's got a clear drain hole, so you can see the blockage here in this picture, so we don't have any more ram air pressure coming in here, which means that diaphragm is not getting expanded with the pressure that's coming in. But we do have a drain hole which acts like a static port in this instance. So if we have a static port here and a static port here, this pressure is going to equalize, which means there's no differential. Our diaphragm is completely collapsed to where it is on the ground. So our airspeed indicator will read 0. This could happen due to icing, so we could turn on the P-dot heat in order to eliminate the ice and clear that blockage. Now block pitot system with clear static system. So what this is you can see that within the pitot tube and our drain hole, it doesn't really matter because our blockage is up here in our plumbing. So in that case, it's going to be frozen at where it's at. It trapped this pressure that's pushing on that diaphragm. So the only way this indicator is going to change is if we change our static pressure. And then we change that by climbing or descending in altitude. And a climb will show an increase in airspeed, and a descent will show a decrease in airspeed. And this can be dangerous because it can lead to a stall in a climb because you're reading a higher airspeed than what you normally are. And you can exceed structural, you can cause structural damage because you're overspeeding the aircraft in the descent because you're showing a low airspeed. If you have a block static system, the airspeed indicator is going to continue to operate, but it's going to be incorrect because we don't have that differential anymore. We don't have the correct atmospheric pressure from the outside to counteract what the ram air pressure is giving us. So it's going to still read, it's just not going to be as accurate. And that concludes my mini lesson for today, and thanks for watching.